If I type in y equals a sine omega t, then what is the effect of changing a? Right, a makes it bigger. So in fact, if I were to plot the function y equals a sine omega t on here, or sketch it even, which is what the assignment's sort of about in a way, if I sketch the function y equals a sine omega t, get something that looks a little bit like that. A represents the height of the wave, doesn't it? So A represents amplitude, which you probably knew, okay? And we can confirm that. And notice that if we change A on autograph, that has absolutely no effect on, just drag this toolbar over here so I can see constant control. Here we go. If I change A, it has no effect on the rate at which the wave, this thing is oscillating. Remembering it's about something that's oscillating. And so the time for one cycle, which comes to about here somewhere, is the same whatever happens to A. So this point here is the same whatever I do to A. Yes, that's exactly right, Ben. So if I were to go back to here, the rotation vector, it's rotating at the same speed, but as you say, it just means that that vector is a bit bigger. Yeah. So the amplitude, the maximum value of this thing that's rotating, is going in a bigger circle. What about changing omega? Yeah. So if I increase omega, what happens to the wave? Yeah. If I make it exactly 2, and then at the moment I'm in, let's change it to radians, which is effectively what we're in. So if I change it back to 1 again, notice the time for one cycle. What is this? So just over 6. What should it be? Well, we'll come to that. Okay, so if I double the rate at which it's rotating, then 3 point something. So the time has halved, which you'd expect, isn't it? Right, pi. Okay, so in terms of pi. So double the oscillation rate, half the time for one cycle. In that same time, if we're just looking at this time here, the same time, I get 2 cycles, not 1, because I've doubled the rate at which the thing's rotating, and so on. So omega represents the angular velocity. So let's look at this function, sine y equals, oh, this doesn't, try this one, y equals a sine omega. Now, of course, on autograph, you're typed in x, but actually what you're plotting is time. So what's going along the y-axis, the x-axis rather, time. So there's the wave function, y equals a sine omega t, omega angular velocity, a amplitude. If we think back to our rotation again, and again this is taking us back to unit 4, one complete oscillation means, one complete oscillation means that it's gone round 2 pi. So if we think about the angular velocity, which is the amount of angle it's gone round per unit time, then the angular velocity is equal to 2 pi, which is the distance round one complete turn, multiplied by the number of turns it manages to do in a second. So let's say it does 1 turn in a second, then it's 2 pi per second. That's the angular velocity. If it does 2 turns per second, then it's 2 lots of 2 pi in a second, and so on. So what's another name for the number of turns per second? Sorry? No, not resolution. Frequency. Okay? So in other words, omega equals 2 pi f, where f is the frequency. What do we measure frequency in? Hertz. And a hertz is a cycle per second, so the number of turns per second is literally what it means. Cycles per second or hertz. So omega equals 2 pi f is a formula. So instead of omega in this function, we could write 2 pi f. What's the relationship between the frequency and the time for one oscillation? If the time for one oscillation is, say, 5 seconds, then what's the frequency? Or the frequency is 1 over the time for one oscillation, if you think about it. So if it takes if the frequency is 1 hertz, then that's 1 cycle per second. So what's the time? It's 1 lot of 2 pi, which is why we got 2 pi for when the frequency is 1. If we double the frequency, half the time, and so on. So in fact, it's an inverse relationship. If I increase the frequency, I reduce the time for one cycle. So frequency is 1 over t, where t is the period of oscillation. In other words, the time for one cycle, measured in seconds. So the period is the time for one cycle. So those are the relationships. So if in this equation I were to write y equals a sine 2 pi f t, that 2 pi f is my omega. So I could rewrite it like that, where omega is the angular velocity. So if you set omega equal to 1, which we did when we first put this in, then from this equation, omega equals 2 pi f. So from the bottom equation, f is 1 over t, omega equals 2 pi over t. What's the time for one cycle? I'll rearrange this formula. T equals 2 pi over omega, angular velocity. If omega is 1, the time for one cycle is 2 pi radians, which is what we saw, isn't it? Okay. So we can get information from here. If we go back to our wave, which is this, how can I read off the amplitude of the wave? If I had an example here, and I was looking at an oscilloscope trace, and I saw that this was 3.6 seconds, and I saw that this was 4.2, and I was measuring volts up here, so that was volts. I could write down what the wave function is. And I'd need to calculate what these values are. So could I say what A was? Right, so A equals 4.2. Can I say what omega is just by looking at the trace? I can work it out though, Josh. I do know what that is. What does that represent? Yeah, the time for one revolution. So that's what I'm interested in. Look, the time for one revolution, which is called the period. So from that I can calculate the frequency, because the period is 1 over the frequency, or I can use this formula to work out omega, because omega is 2 pi over t. So what is omega? Calculate it for me, somebody. 3.6 seconds, yeah. So omega turns out to be 1.75 radians per second, so therefore, for this wave, y equals 4.2, was it? Yeah, 4.2 sine 1.75 t. And I can get that wave by looking at a trace. So, no, what I'm saying here is this t is the variable. So if I plotted y against t, this is the trace I'd get. How do I get these values, omega and a, by looking for the time for one cycle and the maximum voltage I get through? So by looking at a trace, I can write down or calculate values to give me the wave function that describes it. The 4.2 is easy enough to get, Josh, but we'd have to do a little calculation to actually get omega, wouldn't we? Yeah, oh yeah, I see what you're saying, yeah. Or yeah, you just look at the trace. Yeah, that's right. Yeah, because by looking at the trace, we get this and this. Yeah. If we go back to autograph, you might find, as I saw over there actually, that if I increase omega to quite a large value, let's put 1 in. So how am I going to do that? 1,000, say. Then I start to see the wave really spread out. So then I would use, and you might need to do that on waves with very high angular velocities, to actually spread out the waves. So what I need to do is let's just minimize this, zoom in on the x-axis. So that's the key button. If I do that, then it stretches the wave out, and then I can actually start to see what one wave looks like, and there it is. So now I could bring this over here and find out what the time for one cycle is, which is what I'm after. Okay, so the period of this wave is about 0.006, that's 0.007, 0.0063. So if t equals 0.0063, using this equation again, calculate omega for me. So it will be 2 pi divided by 0.0063. Back to that autograph, or up here. Yeah. Okay. There you go. 0.0063, I think we had, didn't we? And you should get around about 1,000. Yeah, right. So there we are. Okay. If I wanted a more accurate value, I'd zoom in further. So I just showed this here. If we want a more accurate value for t, what do? I use my zoom box as normal and zoom in on that value, and so I can actually estimate what the period is. To get what? The period? Yeah. Oh, true, but if I didn't know, if I was looking at an oscilloscope trace and at that trace, not autograph, then I could find out what omega was by looking at that point. That's what I'm trying to say, okay? You wouldn't necessarily know what this was. You're trying to find this. So you wouldn't know that that was 1,000. You divide 2 pi by the time for one cycle to get omega. Right, Ed? You see what I'm saying here? No, yes? Yeah, okay. So if we had this wave on an oscilloscope trace, we would adjust the y-axis. I'm trying to remember what that's called. The y gain, okay, the voltage gain, so that we can actually see the whole wave. It's off the screen. So the first thing to do is adjust the gain so that we can actually, in fact we want to zoom out, see what the maximum value is. So that's one thing. Okay, now I can see that it looks as though it's around about 30 odd, if we were measuring voltage here. Okay, 30 odd volts, 35, something like that. Okay, but I could zoom in on that point. Now I want to find out what the angular velocity is, so I need to know the time for one cycle. So I zoom in until I see one wave. Keep going, stretch it out. Here we go. I'm interested in just the time for one wave, so I'm interested in that point. So this is what I was trying to say, Ben, okay? You can't just, to get this angular velocity, we need to know the time for one cycle, which is this point here. Yeah, we can estimate it by, that's about 0.003, so it's about 0.0025, but we can zoom in and get a more accurate value for it as normal. So if you're doing the assignment, by the way, and you're zooming in on this thing, put this, the wave, in your assignment. It asks you to do that anyway before you zoom in. Usual sort of thing, okay? And then you can zoom in on this value, look, and get the time for one cycle. I'm not sure I've got the right point there. Actually, I wasn't expecting to go that way. So let's zoom out again. Was I looking at the right part of the wave? Yeah, I was, so that's okay. Okay? Right, Ben, does that answer your question?